Okay, let's start. Um, so let me tell you what the structure of the exam would be, and that will help you focus the remaining time on studies, and we're going to just discuss on those. So I'll have three questions. Question number one is going to be on wireless low power. Okay, so we talked about a bunch of different methods which looked at um, how to achieve low power wireless. So this one is going to explore numerically. Okay. Question number two is going to be on naive base, walking you through an example there. So make sure that you are comfortable with that. And question number three is going to be basically a bunch of short answer things examining facts. Okay. Uh, so essentially, after the midterm, we covered wireless, we covered kind of what I called it sense making, and during the course, we kind of learned about a variety of things, Bluetooth, and a whole bunch of other stuff. So this one is going to be kind of a catch-all coverage of that. So let's start with uh, on the wireless side a little bit. So let's refresh the memory. So what were the different things that we looked at in terms of wireless meets energy? So one of the very first things, and I'm going to kind of just revert to the slides, was that if you think about the way the radios work, you have sort of the electronics, you have the fact that you have to amplify the signal so that you can transmit it over the air. Then it goes to the channel, and usually the channel subjects it to decays the signal in some manner. So in vacuum, it's 1 over d square, and I made references to that how for other scenarios like urban settings or close to the ground, there are other kind of models, but they all roughly take the they're like some 1 over d to the power n as a first order model. Okay. So for example, if you take two wireless devices and you put them up in the air and have them talk to each other, it's going to be something like d square modulo some um, reflections and all. You take the same two devices, put them on the ground with their antennas not rising much up. Earth is a good conductor, so essentially the signals going through the conductor get suppressed. So it turns out that the very same device close to the surface are going to see 1 over d to the power 4. Okay, so what this just this basic insight then had led us to uh, look at um, firstly thinking about what the energy consumption is, and for transmitting a bit, one of the first order model. Just give me a sec, please. So this is a good first order energy to transmit bit. And energy to receive a bit, what do you think it would be? There's no distance dependence, so it would be some constant term. So if I were to look at receive, then E bit is some number gamma, let's say. There's some fixed number. And this is uh, given a particular radio speed, and also I'm kind of ignoring some of those things. And between short distance and long distance radios, the real difference comes out to be is how dominant this term is. So the distance dependent term. So for long distance radios, um, the distance term dominates because you have to send the bit over a long distance, so you have to transmit it at a higher power so that after that decay, it is still received with an acceptable power. Whereas for short range radios, the electronic term dominates. And then depending upon the type of radio, alpha versus gamma, in many cases, the gamma dominates. So receiving a bit may be much more expensive than transmitting a bit. So that brings a bit of a change in mindset for very short range radios, which is you cannot just passively listen, which is normally what is done in long distance radios, because listening is cheap, transmitting is expensive, so you transmit rarely, but you optimize, you kind of stay up listening for the transmitting. So, so that's one. So this kind of led to, if you recall, kind of a few different ways you can approach minimizing or making radio communication more efficient. So first is that if you are in a short range scenario, then your strategy, distance doesn't really matter to the first order. So your strategy is one of minimizing the time for which things are going to be up, because electronics is dominant, and moreover receive dominates. So to the first order, then your strategy is going to be shut things down, which means transmit as quickly and then kind of go to sleep. And we had a challenge that if the receiver is sleeping, then how do we wake that up? And we had looked at some protocols for doing that. If you are in the long distance regime, on the other hand, then you are on this side, and there we do the equivalent of scaling for speed. So you transmit, you take more time, and you operate the radio on a more energy efficient basis. And we had counterparts of this, if you recall, in the early part of the course, when we were talking about processors and all, also shutting down versus lowering the voltage to run them slowly. So those are two high-level things. And additionally, going back to this picture out here, we also had the notion that I don't necessarily need to go single hop, right? So if let's say I have a transmitter here and I have a receiver here, and the radios will be characterized by now 3 parameters, right? Alpha, beta, and gamma. Let's look at the table that I had on one of the slides out here. If you look at alpha, it's kind of a nanojoules kind of thing. And then the distance term kind of depends upon the type of radio that you are talking about. And this is short range radio, so it's not dominating. For long range radio, it might dominate.
Is alpha related to the transmitter electronics?
Yeah, it's basically electronics. So it's like the algorithm you are using to encode the data, modulate the data. So it's just that. Whereas beta is purely what, the efficiency of the power amp, right? As well as sensitivity of the receiver. So I have two different ways of messing around with this term. One is I can pump out more power, or alternatively I can make my receiver more sensitive so that for the same power it can still receive this. Same received power. Okay, so going back to this picture then, the very first thing that one would think about, if my goal is some sort of a, let's say, a sensing device which has to transmit to some sort of a thing, the first thing is that am I just purely in terms of number of hops, am I sufficient or not? So if you look at, if I were to send things into a single hop, and then usually this receiver is going to be some, let's say, plugged in device, and also if that's the case, we don't care about it, but it may itself be a reception device. It could be like your Hexaware and your phone, in which case the phone is a receiver, you're kind of worried about both. So first question which comes up immediately is that, is this single hop sufficient? So looking at this picture, what's going to happen is that every bit the transmitter sends is going to be, and the assumption made out here is that this guy is intelligent enough so that it sends it at just the right power. So radios tend to operate in one of two modes. One is that they operate at some Dmax, that is, we select a range and say the radio has this range, and we just pump things out so that any receiver within its range is going to receive it. And the other one is that the radio is smart enough that depending upon which destination it is talking to, it's going to transmit just at the right power. And usually there are protocols to make that happen, transmit power control protocols. But be what it may, let's imagine that the radio has that intelligence, it can do it this way. So now if you think about what happens if I were to, instead of sending on a single hop, I were to send it on two hops. So now I've introduced the second device, which could be yet another sensor in my home, let's say. So maybe my door sensor talks to a motion sensor, and the motion sensor talks to the. So at this transmitter now, and this is d over 2, right? So at the transmitter, the energy consumption is going to be alpha plus beta d over 2 to the power n, right? What about this guy? So this is acting as a relay. So it has to receive and transmit. So it will have to pay reception cost, gamma, and it will have to pay a transmission cost. So now what we have done is this guy is going to have alpha plus beta d to the power 2n, whereas this guy is going to have alpha plus gamma plus beta times d to the power 2 to the power n. And let's assume for the moment that alpha and gamma are tiny. We are looking at, let's say, long range things. Then it's very obvious out here that we are going to come out ahead with the values of n that we normally encounter, right? I mean, even at n equal to 2, you're going to be ahead, and certainly for n, which is 3 or 4 or something like that. Gamma is a receive energy per bit for the reception. Okay, so because reception is distance dependent, so I can just model it as something constant.
At the receiver, it will become gamma for n.
At the receiver, it's just going to be gamma in that case because it's just receiving. At this guy, it's receiving and sending, so that's why it's alpha plus gamma plus beta.
So at both it's the same, but it's just the magnitude.
Oh, okay. Okay. Kind of hand waving out here. I mean, if the radios are different, then the values of alpha, beta, gamma may differ, right? I mean, so that will depend upon the specific hardware. But let's assume here, if all the radios are identical, then what I'm describing is true. If not, then you'll have to pay for it. Okay. So main thing out here is that multi-hopping, at least in the case where alpha and gamma for minuscule, certainly helps. But then if you start, and then now you can play this game further, you can say, what if I had two hops? Yeah, like two relay nodes. Okay, so then it will be d over 3. Same logic applies. Do you think I can keep doing it forever? What will put a stop to it? Alpha and gamma, right? I mean, alpha and gamma become part of it, right? So kind of you can think in terms of there would be some sort of optimal number of relays that you can find, and a very one of the ways to think about also is that what is that characteristic distance d char at which single hop is no longer the optimum, because at that point you're going to switch over to multiple hops. Um, so multi-hop wins out, but there are problems with this. Besides the fact that we can't keep doing it forever, what am I losing?
Cost of hardware, maybe.
Okay, cost of hardware. Although in many cases the hardware is already there, right? I mean, you have a system where a bunch of sensors and all, and instead of now all transmitting back to the central gateway, you're just uh, those relays are already present. But still, agreed that that hardware needs to be somewhat more sophisticated now, right? It will have to run this relaying protocol and all. Huh? You add to the latency, right? Each one of these relays are going to take some time. Okay, so that's another one. Again, the third one is one of those things that why should an intermediate node help out someone else, right? I mean, there is, would you like your phone to transmit my phone's data to the cell tower? There is always this like lending your resource to a third party, and that creates issues as well. Yeah. Um, what other issues do you think? Yeah.
Now that you have multiple nodes, do you have to worry about how they all communicate with each other? Like
Yeah, so the routing. So let's talk about the issues, right? Why lend energy? Latency. Routing. If I were directly sending to the central point, the routing is basically brain dead simple. I just send to that guy. But now I have to figure out which path to take, right? I mean, so I have to do that.
yeah, more potential for collisions of messages.
Yeah, so that's an important point also. So one thing which is very um, unusual about wireless in a way is that collisions matter at the receiving point. Okay, so now let's think about, let's say I had created, let me create another fresh page.
You may also face the issues that we are facing with short range communication now that this long range is divided into a bunch of short range.
Yeah, but that is why the alpha gamma become the bottleneck, right? I mean, at some point after you have had several hops, you are effectively in the short range, and then alpha gamma dominate, then you can't keep doing this thing. Okay. So that's why you have an optimal number of hops, in the sense that if you increase the hops, then even from an energy perspective, you're worse off. By the way, another thing to note out here is that these relay nodes become the bottleneck. And if you think in terms of a network, which relay nodes are going to be the bottleneck for the network? The ones which are closer to your sink, right? Because they are going to be receiving everyone's traffic. So that becomes an issue. But going back out here, let's imagine that I had a long line of hops. So this guy is sending here, this guy is sending out here, this guy is sending out here, this guy is sending like that. Now let's focus on this guy, node X. When he's transmitting, then his packet, his goal is that this node Y should receive it, right? Now let's think about it, what the implications of this are. This guy's transmission, barring some very directional antenna, are also being heard by this guy, right? I mean, it's free space, so things can go either way. Which means this guy, at the time when this transmission is taking place, cannot receive a packet from this guy, right? Because when he transmits, he kind of creates a conflict in an entire sphere around it. And in particular, therefore, this node Z is locked out, and therefore this original transmitter T, its transmission cannot go to Z. Okay, so this multi-hop kind of takes away from. It's not as if I can do simultaneous transmission on every hop, right? Because when X is transmitting to Y, then T cannot transmit to Z, because X is creating conflict at Z. So let's say my radio speed was whatever, a megabit per second. At what rate can I pump data through this chain? And third, right? Because this transmission cannot take place. This cannot take place because there's nothing happening out here. So it's every third hop that I'm transmitting. Okay? So multi-hop creates, so going back out here, there is also a capacity issue which kind of comes up. So multi-hop has all these complexities, right? I mean, yeah.
So on this note though, wouldn't stuff like frequency domain, multiplex and all that-
Excellent. So I could separate them out, right? I could do something so that while X is transmitting to Y on one frequency, P can transmit to Z in a non-conflicting manner. Non-conflicting would mean either a different frequency or a different spectrum code, which kind of serves a similar purpose. Okay, so absolutely. So, but you have to deconflict. If they're sitting on the same channel, so to say, then they're going to collide. Okay. So that creates kind of a challenge also. So when you now kind of think about like, okay, so I have some random network which I've kind of deployed. So first issue you face is how do I figure out the topology, right? And also, do I just go to my like see this idealized situation of just the optimum number of relay nodes being placed for you is never there in reality, right? I mean, the nodes are whatever they are. So part of the system software will have to figure out, do I talk directly to the sink or do I go through an intermediate node? And if so, which intermediate node, right? All those kind of questions essentially sort of need to get answered by the routing protocol. It has to kind of do some sort of optimization to figure out the routes and all. And that can take a lot of time because you're essentially talking about coordinating things all across the network. And in fact, in many of the systems that we encounter commercially at our homes, it can take minutes or even more. Okay, particularly when nodes are also, by the way, sleeping, duty cycling, those kind of things, right? I mean, so it kind of just adds things up. Anyway, so going back out here, so this multi-hopping is a tool at our disposal. So what that leads to is, going back out here, we had shutdown, scaling. Scaling basically refers to that my radio somehow is giving me a knob so that by coding data or stuff like that, I can play this game of sending data more slowly, but taking less energy. So shutdown, scaling, multi-hopping. Those are three main tools at your disposal. What else? What other tools do we have at disposal? Mm-hmm.
Does it depend on the allowed time or does it depend on the distance for both?
It's really about it is for a given distance. So the question is the following: I'm trying to reach out to some far away node because I'm distance limited, and my question really is that is there some knob available so that I can get the data out there with less energy, okay, and less energy on this the transmit power that I'm using. And there are many different ways the radios can provide such a knob for you. And a very common one is you use a more complicated modulation scheme. Or another one is that you can spend more power compressing and then you have less data to send, so you don't win out that way. Or you use error coding, okay, which can help. So there are a variety of ways that knob can come to you, but you're operating for a given distance. I'm optimizing, right? Because I know the destination. And this is something that you encounter quite a bit in radio standards you encounter around us, like Wi-Fi, for example, or cellular. They routinely kind of switch the data rate at which they are transmitting. And So many a times you are better off in terms of effective energy per bit. So let me clarify that. Let's say I'm sending the data to a particular node, and let's say there is a probability that the bit loss will happen. So let's say my radio link is nominally a megabit per second. You could translate that megabit per second into packets and the payload of the packet. So I kind of take care of overhead and all. I'll have some effective nominal throughput. But the problem is, if I'm sending things at a higher data rate, then I'll be using either modulation schemes, which can carry more bits into the same time unit, or I would be doing less of error coding. In either case, I'm increasing the probability that the packet will not go through. And therefore, in terms of energy per bit, which actually makes through expected value, you will come out behind, right? Because a lot of your bits are just getting lost. So you may actually be better off slowing things down. And by slowing things down, you basically gain some time, which you can now utilize towards either using less aggressive modulation or doing more error coding. Okay, so that's really the play that is happening. So you really need to think in terms of what's the information I'm getting across, not simply kind of the bits which are appearing over the channel.
The energy per bit is at the receiver, the cost of transfer.
Doesn't matter. It's both ways, right? I mean, because from transmitter is obviously the transmit side, and but for the receiver also, if it spent time receiving a packet, but the packet was crashed, then it's wasted energy also, right? So one notion which we did also encounter along the way was what I had referred to as good put. And there are variety of factors which come into play. If I look at a packet, then the packets have different kind of headers, and we talked about they had this preamble which is used for clock synchronization and all, and then there is header information for addresses and all. So the actual good bits going across is the rate at which the channel is operating, let's say a megabit per second radio, multiplied by some fraction f, where f relates to, at the very least, the payload divided by the overall length. But then you also have a probability factor because the packet has a certain chance of being dropped. And so you have to really look in terms of what's the expected number of packets which are going through. So for every bit that I need to send across, how many bits I really need to send on an average. And one thing to bear in mind is that the way these packets work is, that you lose the whole packet. So so usually these packets use some sort of a error correcting code. And that code typically would have some limits, like maybe it can correct for a couple of bits. So when bad things happen, even if 1 or 2 bits are off, the whole packet is discarded. Or should it be discarded? Can you imagine? So let's imagine I'm sending packets and some bits go bad. The traditional notion is, yeah, packet is bad, it fails error check, we discard it. Do you think you can make use of it in some cases? Well, error correcting is already taken into account. So your error correcting code said there is error, but I give up. So these are error correction and detection, right? So now you're getting a notification that there is error detected. Okay. Do you think for some kind of data you can still make use of it? Right? Sensory data is actually kind of like that, right? I mean, if I give you a waveform or something and a few bits here and there are wrong, it's very different than if I'm sending a file with program code or something like that, right? Where a bit can be catastrophic. But for sensor data, you have a natural resilience. So one can kind of make use of those kind of things, and people do. But main thing is that you're really kind of all these factors coming into play. There is the overhead of the header. Actually, before that, another thing we had talked about was if my radio was sleeping, then there is a startup time. So startup time, header, all of those things come into play, and therefore the actual fraction of the information that is going through is a function of kind of all these things, right? I mean, so bigger the, so if my policy is if the packet, if a bit is bad in the packet, I'm going to discard the whole packet. And the other situation is packet collides. When packets collide, then they're lost anyway. So yeah, if my bit error probability is p, and let's say my packets are of length n, then the packet error probability is going to be what? So again, let's say the probability that each bit can be lost is p. I have n bits in the packet, right? I mean, so, but more importantly, now you would see that there is an exponential blow up there, right? So big packets have a hard time going through, but small packets have a higher header overhead, right? So small packets more likely to collide or have error. Okay, and it's the tension between these two which kind of plays out, right? Because too small a packet is not good, too big a packet is not good. And your goal really is to kind of maximize the information flow under these settings.
In the equation with RFP, R is the rate.
Don't take it literally. So F is basically, okay, so R is the native rate. F is the fraction, let's call it the overhead term. Okay. And this is the probabilistic term, which is saying, is the packet, what was the probability of the packet? Okay, precise expression for these. Okay, but it's kind of simple algebra at that stage. Yeah.
Going back to the original, when you don't make the trade-off between sending quickly and shutting off and sending for longer and doing more modulation.
So obviously, very roughly speaking, we are saying that long distance, it is the scaling approach, and short distances, it's a shutdown approach. And for certain kind of radios in the short distance, it's the receiver which dominates. Okay, so there are kind of these two subcases there. Okay. Now, precisely what that boundary is a little bit tricky to say because radios are never made using identical technologies and all. But current, I mean, if you were to force me to say a number, it would be somewhere in tens of meters. Let's say 50 meter, 100 meters, something like that. That's where the transition point is.
I mean, is it because of the electronics that the receiver power goes up, or is it because of for short range radios?
Well, so obviously electronics consume stuff, right? I mean, power. And at the same time, if you're really short distance, radios are operating at milliwatt or some milliwatt transmit power. So electronics kind of just begins to dominate at that stage.
Would that be a relative measure? Like if you're doing more encoding and modulation and stuff?
True. So harsher channels, higher rates, all of those things boost up the electronics, right? So so they come into play. Yeah. More complicated protocols, more complicated algorithms, those kind of things come into play. Okay, so those were kind of the three main strategies that we discussed. So again, scaling, which we didn't go into much, shutdown, which we did, and I'm going to talk about that because that was the whole duty cycling thing. And multi-hop, I guess I had a couple of slides in the main lecture, but kind of the main idea is that under some circumstances, putting in relays is going to help you.
On the previous one, usually short range radios deploy modulation schemes that are really energy efficient.
Actually, to the contrary, some of them use insanely bad modulation schemes. Okay, and the reason they use insanely bad modulation scheme is because they're cost constrained. Okay, so that's why kind of it's very hard to make general statements out here because when you go towards simpler radios, they also end up using inferior architectures. Okay? But in theory, yes. Okay. Um, in theory, they would, and in many cases, they do. So one of the other points which I had alluded to during the main lecture, that these amplifiers, remember, their efficiency matters a lot. Now it turns out that some of the modulation schemes which pump a lot of data through that high capacity, they also require amplifiers which have good linearity characteristics, and therefore they are less efficient. So it's a when you're thinking about these things, it's kind of a complicated co-design of multiple things going on. Okay, if you make your algorithms or underlying coding schemes too complex, then your digital electronics blow up. Okay, if your channel is harsh, then your receive algorithms blow up because they have a harder job extracting data from noise. If you use very low simple radio circuits, then oftentimes they have intrinsically less efficient energy per bit. We, by the way, saw the same thing in processors also. If you recall, very early on in the course, I had given these examples of like big dot little, right? The big processor, tiny processor, and the big processors were actually much more efficient in terms of energy per unit work done. It's just that that efficiency would manifest when they were when we could keep them satisfied, right? I mean, if I were kind of a big workload, okay, whereas so that's the tension which kind of plays out, and we see pretty much the same thing in radios. Complicated radios are pretty good at energy per bit basis, but that manifests itself only when you are sending lots of data. And so Wi-Fi actually, if you compare just energy per bit number, I mean, Wi-Fi radios are now what, gigabit per second or 500 megabit per second. So if you compute their energy per bit, it's actually much, much better than the Zigbees and the Z-Waves and all. But it is only if I'm able to keep them pumped in with data. If on the other hand, I'm running a temperature sensor which is sending out a few bytes every few seconds, Wi-Fi radio would be just an awful choice. So one has to kind of match these things out. And unfortunately, architecture methods, which in this case would mean your radio architecture, buys you sophisticated architecture by lead to better efficiency, but only at higher rates, so to say. And that kind of. So the kind of question that I would have out here is to explore like what's the most energy optimum point, and you can basically there are 3 or 4 techniques out here. Okay, so you should be just comfortable with some simple kind of example. So let's say multi-hop scenario. I can give you something, give you the alpha, beta, gamma, ask some questions about it. Okay, the other scaling we didn't go into much, but I can give you a scaling model. So now I can say, look, imagine this radio where you have this choice of a knob. Okay, just remember for voltage frequency scaling, I had said it was. Anyone still remembers? What's the power of a processor as a function of voltage and frequency? V square F, right? Yeah, V square F. By the way, just as an aside, on midterm, a lot of you just blindly applied that formula, okay? And you got it wrong because there in the question I had given you a specific table. So the actual power consumption, I mean, V square F is just an idealization. It's V square F plus the other term which comes as the background baggage. And if you just applied the formula, you're missing on that. So in that particular question, the most optimum point was not the least frequency, which is the one which would have been V square F. It was actually, I think, the number 3 or 4 on the list. So just wanted to point that out.
Anyone get that one right?
Yeah. Many people got it right. Yeah. But many didn't, obviously. So, but yeah. Okay. So just like there we have voltage as a knob, here there are other knobs. Okay. So that's something to bear in mind. Now, shutdown So we talked a fair bit about shutdown under the guise of duty cycling, right? So if you recall, the scenario was something like the following: that our network, I'm sending some bits, and the challenge really is, and that comes in this whole shutdown thing, is that how do I wake things up here, right? I mean, there are obviously all sort of other issues, some of which we explored in earlier in the course in context of processors. When is it worthwhile to shut down, all those kind of things and all. But here, actually, the even more pressing challenge which occurs in radios is that, unlike a processor where the wake up event happens locally, an interrupt signal or something like that, or a timer signal, here the signal can only be received if the radio was up but the radio is asleep. So therefore we have to kind of mimic the effect of a process like this, and the way we did it was that we are going to arrange. So essentially, I have some node which is going to send an event which is occurring rarely. So it's like our wake up event. And what we want to do is to make sure that the receiver does receive it. So fundamentally, the challenge arises that I have to make sure that when the rare event is actually transmitted, then the receiver is able to receive it. And a common way that we shut radios down, so in case of processors, the shutdown wake up strategy is basically go to sleep, interrupt comes, wake up. Okay, and whether you pre-wake up or wake up upon receiving the events, they have kind of different trade-offs, but that's the basic strategy. With radios, what's commonly done is that we duty cycle the radio. That's one of the strategies. So essentially, the radio once in a while wakes up, listens, is there anything for me? If not, goes back to sleep and repeats the process. And in general, the wake up times across these different radios are not going to be aligned. So in this example, B and A are waking up on a periodic basis, and let's assume that they had good enough clocks that they're basically waking up at the same period. But when A has to send the event, the challenge is that how do we get it across? So there are a few different ways that we approached this thing. One was to make sure that they wake up simultaneously, right? Because if radio wake up were time aligned, then all A has to do is to wait until the next episode when the radio is going to be up, and then transmit, because it knows that the other party will also be up. Yeah.
So why did you mention that they have to have the same period?
Actually, they don't.
Okay.
They don't. But so you can certainly work out a scheme using that. It's just usually it is done to keep the same period over the network, just out of simplicity. So you're right. You don't strictly need it, but you need to have some way of knowing what is the recipient's wake up period. Okay, so it could even be based upon that maybe all odd address radios have 1 second period and all even address radios have a 1.5 second or something like that. But it's usually not done. So that's why.
But we maintain the gap between B and A to be constant.
Well, effect out here is like that, but as also you saw in Fatima's lecture on Tuesday, clocks drift and all. Okay, so the reality is much more complicated, obviously. But in an idealized view, or at least you can say in somewhat short time intervals, I can assume frequency is stable enough that that's not an issue, or I just cannot budget for it. So usually when you do need to know something about the hardware, in the sense we'll say, this is the type of clock being used, so much drift will happen, and we had talked about the notion of guard band. In fact, I think I included that slide out here. Yeah, so you kind of budget, you budget some excessive time during your wake up to take into account possible clock drifts. And of course, the other option is to use better clocks, but then better clocks come at the cost of more energy, which is what we are trying to save. So that's the tension. But as I mentioned, that one of the impetus for chip scale atomic clocks was precisely radio power management. So military uses ad hoc networks exactly of the type that I'm talking about quite a bit. These are soldiers carrying stuff out in the middle of the battle theater, and battery supply to keep the army up and running is actually a serious logistic problem. So the hunt for keeping whatever radios and all energy efficient has been has always been a challenge. I mean, there's a lot of money over the past 3-4 decades that has been pumped into that. So back to our problem. So one approach is I keep things synchronized, right? And that was actually approach number 2, the way we had presented. So what happens now is that once in a while we have a special wake-up episode where we exchange time. So everyone kind of gets to know how far apart they have drifted, and they synchronize it. And after that, until next episode, we are operating in sync. This is essentially you can imagine during this time some version of the scheme that Fatima spoke about might happen. Okay, maybe one of the entity can broadcast time is X, or maybe there'll be some back and forth to figure out how much the clocks are drifted, but we synchronize. And then until the next such episode, which might be minutes later or hours later, we keep in sync. And now all A has to do to send the event out is it has to wait until the next wake-up episode and send the packet out. Obviously, there's a latency challenge out here, right? Because I have to wait until the next wake-up episode. So whatever is my duty cycle period divided by 2 is the expected latency. And then if you are sending this thing through a network, then there is a potential latency issue in each one of these things. But there are sometimes optimizations done where the packet can just race through. So the whole network has woken up, and we make use of that opportunity to just kind of bubble through the packet instead of repeating this process every time. But generally speaking, you will, in something like this, you would expect, if you are unable to immediately send the packet out from B to C and C to D, then you'll pay a latency which is equivalent to this period on each one of the successive hops. So latency is a challenge, and then there is an initial latency out here, which is simply you have to wait until the next episode. Okay, typically the kind of clocks and all that you encounter and all result in that you resync every, let's say, I guess I put 15 seconds out here, but let's say order of a minute. Okay, but again, it's a function of the clock. Okay, so prior sync is one, and the other approach is what is called as preamble sampling, and that is equivalent to, like, I call you, how long should I let the phone ring so that you will come to the phone, right? If I let the phone ring only a little bit, then you may not pick. It's the same concept out here. So what's happening here is that A now goes ahead and starts transmitting the packet immediately, except what it does is it sends a large or rather a long preamble. And the preamble it sends it's long enough so that B is bound to wake up during this period. And assuming that the whole network is designed to perform a period, then essentially this means that this preamble should be a period plus whatever is the minimal preamble needed. That much long. There's a preamble, and then what will happen is B will wake up somewhere during this period. In this case, it woke up in the middle, and it too will stay up until the payload arrives. Okay, so yeah.
But your A sense, I mean, while it's sleep, I mean, just every time there is a depot that wakes up like the small period.
Yeah, both of them wake up, but they just listen, right? So whenever all the nodes, all they're doing is they're periodically waking up, listening. Once in a while, one of them will have something to transmit. Okay? So if you compare with the synchronous scheme, in the synchronous scheme, we are paying the overhead of synchronization. Remember, even if I had no message to send, every 15 seconds, I'm doing some message exchange, right? So there is a background communication which has to happen to keep the network in sync. Whereas in this scheme, there's no transmission happening. All you're doing is waking up, listening, going back to sleep. So if there was no event happening, there will not be anything sent out over the air. Which has, obviously, I'm not transmitting anything. That's one advantage, although you could argue that if it's a short-range network, not transmitting is not that big a win because I'm losing energy waking up anyway. This wake-up time could be pretty tiny, whereas the packet transmission time may need to be long enough. But the other challenge also is that in many settings, you want to keep radio silence. But again, military networks and all, they don't want unnecessary transmissions going out because that means the enemy can hear it and then jam or attack or whatever. So that's the penalty in the other case. Whereas here, nothing else is happening. But the flip side is when we are sending the packet, we are occupying the channel for a longer time, right? And therefore spending more energy also. So async, now let me create a sync approach, constant background traffic plus energy to maintain sync. Whereas async, the disadvantage is that longer packet communication time, right? So no sync, but so which one, what do you think will be the factors which decide one versus the other? Like under what circumstances do you think you will use sync, and under what circumstances do you think you will use the async approach? No. Tell me in terms of like why, what characteristic of the data matter in that case? Is it just periodic? What if it's periodic once a day versus periodic once a second? You think that matters?
More common you send messages, better synchronicity.
Yeah, exactly. Yeah, so if the data is going to be naturally more frequent, then might as well use sync because in fact, if data is sufficiently synchronous, I may not need explicit synchronization packets. I can just make use of the data packets to opportunistically also synchronize, okay, because synchronization is just some additional timestamp there. So higher rate scenarios, sync, maintaining sync is the preferable approach. Whereas rare occasional data, which often happens in things like, I don't know, like the front door sensor in your home, I mean, it triggers once or twice a day, right? I mean, when you're leaving, coming back, or in case of military settings, they may have sensors for perimeter defense, and intrusion happens, then you want magic to happen, things to be done rapidly, but most of the time, the sensor is just there. Now, even in asynchronous networks, it's not as if you will never send any packet until the next event. I mean, the reality is that you also need to make sure that your sensor is alive. So usually there is still some packet sent once every so often, just to do a sanity check on the network. But that hopefully is a lot longer, maybe once a day or once a month or something like that, right? I mean, just sufficiently long enough. Okay, so there was a variant of async where instead of sending a long preamble, we would send a chain of packets with minimum preamble, and then in some cases have a little gap so that an ACK could be done. Question?
I have a question actually about this one, right? So it's not a very short preamble, right? And the RX is ready for just like a sliver. If it gets ready when we're sending data and not the preamble,
If it gets in the middle of the preamble,
yeah.
then it would see junk. basically,
And
because
does it wait to-
yeah, so it will wait. So basically, what the receiver does is it basically will say, there is energy on on the channel. Let me take my correlator and keep matching, and the match will only happen in next 10 p.m.
Okay.
So, and then there is yet another variant where in between packets we leave a little bit of a time so that this guy, the receiver, can say, hey, I received the packet. And all of these things are playing around with the latency energy trade-offs, basically, right? Okay, so that's basically what's happening out here. So again, what I expect you to be able to do is to reason about what kind of the latency numbers are you might see under different scenarios. Okay. So this is the shutdown mechanism, and in particular focusing on how to wake up a sleeping radio. Okay. Then we had the issue of the guard band, which is that as time progresses, so again, if we go back to our synchronous approach, for example, we synchronized at this purple episode. And then now we are operating open loop. But as we are operating, the clocks are drifting apart. So as we keep doing it, so the first time instance, A will say, A and B say, for us to make sure that we are up at the same time, we have to budget for some error margin, right? So let's say this period was T, nominally. But let's say our clocks are such that there is a relative drift of delta per second, delta second per 1 second. That means that by the time I reach this point, the drift would be delta T. And therefore, I need to budget out here because I may be waking up delta T ahead or I may be waking up delta T behind. So I just need to fatten the time period that I'm up for. And then as we keep progressing, that time keeps increasing, right? So since the last sync, how much I could have drifted, you budget for that, and then you use that as your guard band, as your excess time, and that directly translates into wasted energy. So what this also means is that your clock, the quality of your clock affects energy. But there is, as always, a complicating factor that if you need clocks with a lower value of delta, then they usually are the more power-hungry clocks. So for example, ordinary crystal oscillators that are used in our electronics versus so-called temperature compensated crystals, which correct for temperature errors. And then there is next category called oven controlled crystal oscillators, which literally have a little oven in the package, which keeps the crystal on a stable temperature. And then finally, you have these things like atomic chip scale atomic clocks and all. As you go up, you go from maybe an error of 10 microsecond every second to maybe a picosecond per second. That's the dynamic range that you across these technologies, or even sub-picoseconds. So, but meanwhile, the energy goes from microwatts to tens of milliwatts. It's the same thing. So delta goes precise. So I want lower delta to get better energy efficiency, but lower delta comes at a cost of clock consuming more power, and that tension again kind of this plays out.
So on this one, we have the transmitter takes into account the guard band, so it increases the time of the preamble sent down.
Yeah, there are many different ways you can orchestrate that. So it could be the transmitter, it could be the, but logically speaking, it's the
The next
transmitter.
bit has a receiver doing
Mhm.
it. Okay. Either side.
Yeah, either side can do it. Yeah, but somehow, somewhere you have to account for it. And the other thing is the way I described right now. I said I will keep changing the guard band with respect to since the last sync. Oftentimes I just pick a guard band and then stick with it all through. So. Okay, so yeah, this covers the point I was making. As you can see, synchronization obviously plays a pretty important role for this purpose, as it does for other places, and they're very broadly Um, this is from Fatma's slides. Basically, there are two ways of synchronizing. One which works in one regime and the other which works in the other regime. So one way is, so let's say I want to synchronize time with you, right? Which is what we were facing out here, right? In the slide. So one way is I simply say time is X and you note it down and you set your clock at the time. The problem there though is that the delay from me to you is some unknown thing. So in reality, your clock will always be that delay behind, but this is acceptable if delay is pretty tiny. Now, usually that would mean is short range, right? So for example, what the speed of light, plus perhaps some other factors and all, but let's say kind of from my radio to a nearby radio, you're probably looking at order of 10 nanosecond or so. The speed of light itself will account for a nanosecond or so for a nanosecond a meter, right? Nanosecond a foot. 0.3 nanosecond a meter, so it's nanosecond a foot. But there is also some additional delay where when the bits are going out of the radio and are being received, so there are circuit delays which also kick in, but you can get to that. But on the other hand, if the delay is large, then that becomes a problem. Now there are two settings in which the delay can be large. One setting in which the delay can be large is you just have to travel a long distance, okay, maybe go through a network. Another setting is that I'm speaking close by, but the other party may be asleep. There may be a lot of delay in the buffering, right? I mean, I may tell the underlying radio, send this packet out, but if it's a duty cycle type radio, then under the hood, it's going to wait until the next transmission episode. And that can complicate things, okay? So those are the limiting factors. But oftentimes, this is perfectly fine. The other complication which comes in is, are you able to do this timestamping which you need at sufficiently close to the radio? Oftentimes, we don't have access to the low-level radio. Like, for example, on my laptop, if I want to write a program to send a packet which is timestamped, if I dive deep down into the OS and timestamp when the packet is being handed over to the radio, or even better, if I have access to the firmware or the radio provides me the ability to timestamp, barring that, if you were to simply put timestamp in the packet and then hand over to the OS, then all that delay in the operating system is going to also manifest out here. Can you think of a way to overcome that? No, you don't have access. If I had hardware timestamp, I would use that. You don't have hardware timestamp. Well, as engineers, what do? We measure, right? So you can pre-measure the delay. It's probably going to be some distribution. You pick its mean, you subtract it away. Okay, so I can characterize the software delay and subtract that out, in which a lot of these systems do. They basically have a correcting factor based upon prior measurements. So if you look at the delay between a pair of radios, you'll usually see kind of a bell curve. Okay, that bell curve is reflecting the cumulative effect of the buffering delays, as well as the fact that these radios are not identical. Okay, so they have some manufacturing differences in the amount of delay they are going to see. Another factor which contributes to the delay is that these are all processors. They're operating at a clock tick. So what may happen is that I'm sending the packet out. It may arrive out here in the middle of a clock tick. So the time stamping can only happen at the end, right? I mean, so there's a quantization error which kicks in. So there are all sort of sources which kind of make this thing interesting from a distribution perspective. But at the end of the day, you can attempt to correct for it. So in many settings, this is fine. And the reason I'm bringing this up is problem number one in the homework. You do have the situation where the Bluetooth radio is not up all the time. So now you can approach it many different ways. One way to approach this thing is that send this information out once you actually have a connection, so that then the delay is minimized. If on the other hand, but you will still face some some delay through the Python stack, because there is no way for you to tell the operating system timestamp it when the packet is going out. You are going to timestamp and then hand it over. So then you can use averaging on top to correct for this thing. Okay, but my suspicion is with kind of so it depends upon how aggressive you want to be. So in terms of achieving visual synchronization, namely 0.1 second kind of thing, I think that should be reasonably straightforward. If you want to minimize the time difference between the two pins, like if you were to observe at the pin level, then you may have to do this kind of the funkier stuff that I'm describing, that you do some averaging, correct it over time. Don't just rely on a single thing. Basically, all I'm saying is that one thing may not give you the good offset state, but multiple measurements might averaging over it. Over the course of the grading your assignment, there's not going to be much of a clock drift, right? So if you think about it, there are two factors at play, right? One is your clock drifts, and the other is just this basic equation has errors when we actually implement it because of all these quantization and other uncontrollable delays. So you should do it multiple times to kind of get an averaging, right? And then again, these clocks in Hexaware and Raspberry Pi are pretty good. They may drift, let's say, 50 microsecond a second relative to each other. I would be pleasantly happy if you are in the millisecond territory in terms of millisecond to 10 millisecond at the pin level, and visual synchronization at the display level. Okay. So a simple scheme can work. You hopefully remember your radio delays are pretty tiny out here. Now, one of the other ways you can kind of compensate for this is doing the bidirectional approach. Okay, and to compensate things out, to cancel things out. So anyway, so that's synchronization. Let's see, what else did we, how are we doing on time? 5:15. Okay, so we had looked at one particular medium access control protocol, which was the one which is used in Wi-Fi. And this is an example of a protocol optimized for radio scenario where listening is cheap. Okay, so and therefore in this case the approach is, whenever you want to transmit, listen. Make sure that no one else is transmitting on the channel for some period, DIFS, and then once you get a channel, once no one is transmitting for that period, then you can go ahead and transmit. What may happen though is that you wanted to transmit and you're waiting in this DIFS period and someone else beats you to it. They can beat you to it either because they started earlier, or they are not using DIFS, they are using something smaller, which can happen for two reasons. One is cheating, that is, you can grab, if you could modify your Wi-Fi radio to get more bandwidth in the Wi-Fi network, first attack would be to use a smaller DIFS. Okay. Or alternatively, there are particular reasons why during the protocol nodes do not wait for full DIFS, but they wait for a smaller time. But in any case, some node wins, they transmit. The other nodes then go back to waiting mode. They keep monitoring the channel until the transmission is freed, and then they wait for some stochastic amount of time, some random number, and then they transmit. Why did we have this random delay? Yeah, there might be multiple people waiting, and therefore, if we didn't have this delay, they will all transmit at the same time. So we want to stagger them out. Okay. And then we also had the challenge that even with this, collision can happen. Collision can happen because two parties may have genuinely started at the same time, or they are just in different parts of the network. So I'm monitoring the channel out here, looking for the channel to be free at DIFS time. Someone on the far corner is doing the same thing. And we both want to send a packet to the middle of the room. So I did it, the other side did it, we both we cannot hear each other. So, okay, we both transmitted and the collision happened in the middle. So to bypass that, the strategy that is used is that if you have really long packets or if you want to be ultra conservative, then you first exchange short packets, RTS, CTS is what they're called, to kind of reserve the channel. So you're announcing to everyone, hey, I have grabbed the channel. And then you send out your long data packet so that the long data packet has a higher chance of going through. So those are the things that 802.11 does in its basic mode. Assuming listening is cheap and all. But then there are a couple of reasons why that is not enough. One is this kind of delay, wait, delay, that kind of approach works fine for some kind of traffic, but doesn't work fine for some other kind of traffic. In particular, it doesn't work well for traffic which is periodic and latency constraints, so like your voice over IP calls and all. And the other one is it requires things to stay up. So what 802.11 also has is this mode where the whole system operates in a periodic manner, and then a time within each time frame is set aside for a collision-free transmission. And then so that's indicated by this PCF, and then the remaining time, DCF, is set aside for that contention-based mechanism. And then finally, within this PCF period, basically what 802.11 does is it does kind of a polling. So the base station, the access point, basically asks, do you want to transmit something? Do you want to transmit something? And then it kind of does a polling. So that way everyone transmits without collision. And so don't worry about the details on this one. And then they have a power management strategy where nodes can go to sleep, my laptop can go to sleep, and then the base station would buffer packets headed to my laptop. And then once in a while, the base station will announce that, hey, I have waiting packets for laptop 1, laptop 10, so on and so forth. And then it transmits them during the special episodes called TIM, Traffic Indication Map. And then when my laptop will hear, oh, there is something waiting for it, then it will stay up and grab the packet. So even Wi-Fi has fair bit of power management capabilities kind of built up. And it too needs time synchronization, and it does the dumb approach that I was describing, which is just announce it, time is this, and the delays are assumed to be tiny enough that we don't really care about. Okay. So when it comes to time synchronization over wireless, it's pretty easy to get into milliseconds. It should be pretty straightforward for radios which are always connected. For radios which are sleeping, then obviously it depends upon how much they are sleeping and all. Okay. So there you have to be careful to do things when you're actually connected. So in case of the BLE1, as you know, there is if you timestamp and then scan, then you are going to have a problem. You should do the connection and then do the exchange. So anyway, that's the wireless thing. Let's see what else. We talked about sender and receiver based approaches. So in case of sender initiated approaches, which is what we saw, the transmitter initiates the transmission. In receiver initiated approaches, the receiver sends out a packet saying, hey, is there anything for me? And then the transmitters get back to it and say yes, then transmit the data. So what's happening in this bottom figure is that transmitter is listening, the receiver sends a probe, and the transmitter, upon receiving the probe, sends the data out. When do you think you would use receiver initiated versus transmitter initiated?
you wanted a receiver initiated for like Bluetooth and stuff where the receiver end is the one that's using more energy, right? So you want it to choose when it wants to wake up.
Right. So the more energy constrained device is the one which should, in that case, a receiver. Okay. So, look, most of these things are just obvious logical implications of the assumptions that we make. Okay, there's nothing terribly deep about any of this stuff. So, faced with any question, just think rationally. That's all that is needed in this thing. Okay. One of the funnel thing we had covered in the wireless thing was this whole issue, which I kind of mentioned earlier, which is if one packet, one node is transmitting and the other node cannot transmit at the same time and all, and so we had this whole latency build-up and error build-up and all, and then there was one cool scheme which was relying on the fact that two nodes, let's say there are two nodes and which want to send a packet to a third node. Normally, if they transmit together, we assume that the packets will collide. But under one condition, that is not true. And the one condition under which it's not true is they transmit exactly the same thing at exactly the same time, right? Because if the two guys, well, to be more precise, they transmit it such that the receiver would get them simultaneously. So let's assume for the moment they're equidistant from the receiver. Okay, so they transmit at the same time and absolutely identical content. Then the interference pattern, it will just literally overlap and the receiver would still get to hear. And then there are more sophisticated versions of these things where I may know something about what the other party is sending and kind of subtract it out. So there are fancier ways of making use of this. But this particular scheme literally just used this very simple idea that the initiator sends out a packet. Then the first hop nodes, which is the ones in the red, okay, they all receive it. Then in the next episode, next epoch, all the red colored nodes transmit, but they transmit the same thing at the same time. And therefore, those nodes which are neighbors of both are still going to be able to decode it. And what this scheme allows is kind of like a single sweep through the network to get the packet out. So very efficient broadcast, right? So fast packet propagation for very efficient broadcast. So broadcasting in particular is a challenging operation in wireless. Okay, the final thing I expect you to know is some of the specifics about Bluetooth, the different ways the protocol messages get exchanged. This is more kind of lively, more an assessment of your grasp of what BLE does or doesn't do, what some of the different jargons are. So just make sure that you're familiar with the thing. Hopefully, I mean, I guess most of you are using communication with Hexaware, so you should be fine with this one. Okay, let's see. So any questions on the wireless part? Yeah. So again, just to kind of recap, you should be able to do some numerical computation around the three schemes that I described. Okay, obviously I'm going to ask one of them. So multi-hopping, kind of shutdown where you have these nodes waking up, and then finally, if I were to give you a model of how the power changes for the radio, then doing the scaling there. Okay, more recently, I guess in the past 3 weeks or so, we covered a variety of things around sense making. Now here, what we saw is a typical, we started with kind of the notion of a typical sampling pipeline. We spent some time on sampling, and very broadly we talked about 3 kinds of sampling approaches. One was Nyquist sampling. What assumption does that make? or another way of saying it
Or
is
band
it's
limited.
the signal is band limited, right? Okay. And what was the goal in Nyquist sampling? Reconstruction, right? Okay. And then then basically we had compressive sampling, which relied on the fact that maybe I can make additional assumptions about the signal. And the example I walked you through was, imagine I knew it's a sine wave. So sine wave only has 3 parameters: the amplitude, the frequency, and the phi. And therefore, really, what I'm seeking to do is to collect enough samples so that I can estimate these 3 parameters accurately. Right? That would be sufficient for reconstruction. I could potentially gain even more if I were to say my goal is not to reconstruct. My goal is to just estimate, I don't know, let's say estimate the frequency, nothing else. Then maybe I could do even better. But in an ideal scenario, 3 points would have sufficed, except that those 3 points may not be nicely located. Maybe I was unlucky and they all sample at the same point. So therefore, you usually need to end up sampling at more points and to get an accurate estimate. So compressive sensing kind of made use of the fact that he may have additional knowledge about the signal. And in particular, in this case, we are saying that, look, the signal is sparse in a parameter domain, right? I mean, if I look at that signal in frequency and amplitude and phase, then it's basically extremely sparse. So we're kind of making use of that fact. And compressive sensing kind of builds upon that idea. So that was the second one. What was the third approach to sampling we discussed? So, adaptive, right? And the notion in adaptive is that I would sample if the signal has changed sufficiently. And in case of space, imagine a robot, it's sampling, collecting, mapping out a space. It's kind of easy to see what may happen. The robot takes a step and it realizes, aha, measurement changed too much. Let me kind of go back and collect some additional measurement. In time, it's a little bit trickier because I can't go back in time, right? So the challenge then becomes of monitoring the signal in the analog domain. And then the moment we realize it has changed sufficiently, we do a sample. That was approach number 1. Approach number 2 was to use a model. That is, based upon recent history, we make a prediction. What is the next good sampling point, right? I mean, so if I see signal was changing very rapidly, then I would be very conservative and sample quickly. If on the other hand, we saw that the signal was changing relatively slowly, or is expected to change relatively slowly because maybe I have access to a model, then I'm going to take a longer step. Okay, so obviously I may be wrong, but think about it this way. Whenever you're wrong, it's not like end of the world because all these systems have noise anyway. So as long as you can keep being wrong sufficiently under control, you should be okay. It's kind of equivalent to, we talked earlier about real-time scheduling, and I kind of presented it as if these deadlines were sacrosanct. And to some extent they are, but on the other hand, in many applications, if you miss a deadline, it will appear as a blip and you'll move on, right? I mean, if it is a video playback happening, and if a frame once in a while is a teeny bit delayed, you'll not notice. So missing deadlines in many cases is gracefully tolerated. Okay, so we talked about sampling. Then the other thing we talked about was inference making, and making inferences out of the sensor data. And yeah, so the thing that I wanted to pointed out was that really what's happening in these things is that the system I'm trying to monitor, like the human being or whatnot, is going through some states which are of interest to me. So these states represent, can take the values of the label I want, right? What activity they are doing, like whatever, running, walking, that was those kind of examples. But we are observing the human being through a sensor, which gives us noisy observations. So we had the example of deployment in the apartment where the individual were wearing some sensors and there were sensors in the environment, and as different activities like cooking and cleaning and all were happening, then the various sensors would pick up data and kind of spit it out. So our goal really, in a way, strictly speaking, is given the time series of measurements, I want to figure out what states I went through. Okay, and there are kind of various versions of those problems, but they all kind of dance around that fact. Going from raw sensor to the state directly, and going from sequences to that often is hard and unnecessary. So variety of assumptions get made. One very common thing we do is we window. So we look at a window and make an independent assessment about that. And the second thing is, instead of working with raw data, we decide on a set of features and we work with those features. The features we work with because it reduces the amount of data, but also very importantly, features are good because it brings some expert knowledge into it, right? I mean, I know that this particular aspect is important. Like, for example, if you're looking at ECG signal, then the doctors look at certain features to be able to make the diagnosis. So the experts have already decided that. So features are, these feature vectors are both expert knowledge plus data reduction. Plus, do you see any other advantages for features?
You reduce the data that you're working with?
I already know that. Data reduction.
Prevents overfitting.
In what ways? I don't see that. Yeah, it's kind of like expert knowledge. Well, the third very important one was that what if my underlying sensors were diverse or were sampling at different rates and all, right? So by going to features, I kind of bring heterogeneous sensors into a common plane, into a common framework. So cope with heterogeneity. A second assumption we make is, in a very common scenario, is that windows are independent. So we make an independent assessment using the data and feature vectors during that time window. Okay. So, but there are obviously schemes where you can take history into account, but this is very common. I'm just going to look at the current part. Classification versus regression. So classification, my output is some labels drawn from a set, like is it an apple or an orange. Regression is some numerical value. What's the speed, for example. And likewise, my features in the feature vector would also be nominal or categorical, or they could be continuous. And one should be able to deal with both. Very important point in this whole story is that sensor measurements rarely give you the state directly. That it's rarely the case that what you are observing out here is going to tell you directly about, oh, the person is asleep or awake or whatever. Okay, it will tell us something about it, but not directly. And we had gone over a whole list of kind of different kind of features and all that are used. So, but they very broadly are temporal, spectral, and contextual, which I have not listed. The most, so there are a variety of classifiers and all the two which we went into in some depth. One was naive Bayes and its variants, and the other was we spent some time on the deep networks. Naive Bayes is the only one I went in sufficient detail for you to actually do end to end. I guess you could also do it for the deep networks, except that they are way too complicated in terms of too many neurons and all. The naive Bayes, the nice thing is that it can be done very compactly. What's the assumption we make in naive Bayes? Features are conditionally independent, right? So given the label, features are conditionally independent. So condition on that, features are independent. So let's take example. Let's say my feature included temperature, month of the year, and motion events in the kitchen, or whatever, occupancy in the house. And I'm trying to predict energy consumption of that house. Which of these features you think are independent? Conditionally satisfy the naive Bayes assumption. So again, I'm trying to predict energy consumption in the house. My features are temperature, calendar month, and the occupancy in the house, number of people in the house. So it's just purely intuition here. So, none. Temperature and month are related, exactly. So there probably your assumption is not going to be true, right? I guess, I mean, if you really want to be pedantic, you would say, but if it is December, it's holiday, people are more at home or something like that. Okay, but ignoring that for the moment, I mean, I think more likely than not, temperature and calendar month are going to be very, very related, and perhaps therefore not good candidates for naive Bayes, but occupancy to the first order is perhaps, yeah.
But in practice, when using naive Bayes, those assumptions, we could still assume that they're
Yeah.
independent.
So in practice, what does happen is that naive Bayes works surprisingly well, even when these assumptions are violated. Okay, but often it doesn't, and in which case we have one or two things: prune away the features which are not good candidates, or use some other method. Okay, which is more reasonable. But the basic idea is a very just driven by Bayes equation. So y is what I want, x is what I have, the features. So we want to find that value of y with given the observation x leads to the highest probability of x. So that we can convert into probability of x given y times prior probability of y divided by prior probability of x. And the way the naive Bayes assumption kicks in is that I can think of x being a d-dimensional feature vector. So I can think of these different dimensions, which are basically different features, like in my example, year, calendar, month, stuff like that. We are basically saying they are independent. So therefore, I can express this particular distribution as a product of the conditional distribution of individual features. And then my goal basically becomes to find the maximum value of this p y given x. And with some appropriate simplifications and the fact that the denominator doesn't matter proves out, I really end up with R max of the product of xd given y equal to k and probability of y equal to k. And the way so our parameters of this thing then become basically these. You might want to think about how many parameters we have in a system like this, but basically there are a few different sources for this information. Either some expert gives to you, or in our case, we have the training data, and you do frequency counting in it to measure these things. But we immediately run into a problem. So firstly, why did we do the naive Bayes? What's the motivation behind doing naive Bayes? Like making this assumption. Let's say we were to not do it. Let's say we were to maintain the original equation, right? That one, okay? And what would be the disadvantage of that?
You won't be able to classify
couldn't use that
Um,
independent calculation using
No, but that's precisely what I'm asking. That let's say I were to not make this independence assumption. Let's say I just keep that original expression, right? So R max of P by X is the same as R max of the numerator, Px is prior constant, right? I could certainly do it that way, but so why do we make the naive Bayes assumption? I mean, I could do the same game of looking at my training data and estimating Py given X and P of sorry, Py, Px given Y and P of Y, right? I could look at the training data and do the same thing. Yeah, it requires too many data. Because think about if X was a vector where of dimension 10, each one of them can take some, let's say, k values, then my space is k to the power 10, okay, and I will need a sample of each one of those, right? And versus I have separated out, and all I'm saying is that I need to have sufficient sample for each value, each of the k values that X takes, and likewise sufficient for each one of the k values that X2 takes, and so on and so forth. And for the same amount of data, I would be much better off with this. So naive Bayes, the assumption we make is fundamentally about keeping the training data size small. Okay. But even with that, we run into problem that for certain values of Pxd given Y, I may not have any sample. Right? Maybe I was unlucky, just that observation never got made. So what we additionally do in that case is, so again, so ordinarily our definition would simply look like probability of X having a certain value and Y having a certain value is basically counting the samples. But sometimes the sample count will be 0, so I may not see it. And once it becomes 0, the numerator becomes 0. It doesn't really matter what else do I have. So this is why we use this additional term, this and this. This is called Laplace smoothing. Okay, and it's basically what it's saying is that I'm going to assume there's a prior already there. Okay, in this case, I'm basically saying that there's a uniform distribution. So you will hear things like use Laplace smoothing with L equal to 1. Okay, so basically I start by saying as if I already had a sample. Okay, and for the denominator, I will have to worry about as many samples as distinct values Y can take. Okay, so so this way we avoid that nasty problem of not having any sample. Okay, and which is kind of again intuitively saying that I'm going to assume that everything had an equal probability to begin with, and then the samples I'm seeing are providing me an additional evidence towards that. It's kind of like the counterpart here would be, I have a coin, you're trying to estimate its probability of the head coming. It may be, so the top version would be, I'm going to flip the coin, you're going to observe it, how many heads and tails I got, and you're going to estimate the probability of head to be number of heads divided by number of flips. Except it may happen, unluckily, but no tail ever. Okay. So in that case, you're basically saying that tail is 0, so it will have no impact. You will get probability of head to be 1, probability of tail to be 0. What Laplace smoothing is doing is saying that, look, I have a prior thing that the coin perhaps is, let's say, uniform. So I'm going to start it as if I had already seen a head and a tail. Okay, and then I'm going to build up from that. Or if I want to express an even stronger prior that the coin was unbiased, I will say I'm going to start by assuming that I've already seen 10 head and 10 tails. That means L equal to 10 in that case. So that means that additional evidence are going to build up on top of that. So it's the degree of confidence you have in the prior being uniform is what will express the evidence. Okay, so applying this thing is basically then going through the data set and basically doing a counting. But the main thing is this thing only works if the way at least we have written out here, it only works if things are categorical, if my features are categorical, things like month of the year or something like that. But if they are numerical, like reading of temperature or accelerometer or something, so you have really two ways at that stage. One is to convert those numerical values into categorical. So you kind of divide them into bins and say it's very high, medium, low, something like that. The problem with that approach is that you are still losing the distance metric between them, right? I mean, the fact that very high is close to high and very high is far from very low, that is being lost out there. So it's better to bring to bear some sort of numerical approach directly, and that is what we like here. The typical thing is that continuous stuff is modeled as a Gaussian variable, some mean and sigma, and now what we do is we estimate the mean and the sigma. Okay, again, given those data points, we do that, and for mean, it is samples you had, summation of those divided by number of samples, standard sort of where you would estimate mean, and then the variance follows in the same manner. So from the data, from the continuous values, we estimate mu and sigma or sigma squared, and then we kind of go back and so this was an example, and then we kind of go back and apply that out here. So for that normal distribution, so in this example lecture, there was one categorical variable which was the day of the week, and the other was a continuous variable which was the energy in the accelerometer. So essentially we restrict continuous variables to be Gaussian distribution and then calculate all the probabilities using that, and instead of estimating the whole PDF of the discrete distribution, we estimate the mu and the sigma square of the continuous. Okay.
Quick question. So, like probability of x pi equal to t given y equal to 1. Such a case doesn't happen as such, but then we substitute the really small.
Say it again.
Like the value for probability of
Like you're talking xy?
given y equal to 1.
Okay, I see what you're saying. What if it never occurs during this? Yeah. So you again can give it a very small prior.
Isn't that
Yeah, that might not happen. No, this is no. Actually, so what's happening out here is we are still estimating the joint normal distribution. So the challenge that may happen is, what if I don't have any samples to give me the normal distribution? But let's assume that you start. Let's say I didn't see that. Then just like the Laplace smoothing, you can start with maybe mu equal to 0, sigma equal to 1, and build up on that. So it's always about prior evidence about what that variable would take, and then the observations are building upon that. Okay. Okay. So that's on this part, I hope you are able to do the nice phase. Feel free if you Google and all, you'll find plenty of examples all over. Just become comfortable that given some data, you can compute these probabilities, but it's basically just counting things. Yeah. Any questions on this?
Is the second example given
Or is it actually right or not?
because
This one?
yeah, in the case of y equals 3, there are only
yeah, it's 1 by
2.
2.
It should be 1 by 2.
So it should be 1 by 2. Probability of x1 equal to 1 given y equal to 3. There are only 2.
This one you're talking about?
Yeah.
Okay. Probability of x1 equal to 1 given that y equal to 3. So firstly y equal to 3, there are only 2. Yeah.
And also, like from Aditya's earlier question,
Mhm.
so in the first one, x bar 5 to 251, do we see that it's continuous and then we do the different sort of measurement and get the probability with that Gaussian?
Yeah, so the Gaussians were estimated in the previous slide. Okay.
But in this case, if you just say x bar 5, then you would see which values of y take that and then you would do the calculation. But there it gives a specific value. I'm not sure how.
No, I don't think I get your question.
No, so like when x power 5 is given a very specific value, like how when we don't have continuous value, we can actually look up to it. But when you have a continuous range of values, how do you actually go about like picking up the samples for the Gaussian distribution?
Yeah, you're saying that I have a PDF and then so this is actually just consulting the PDF. It's looking at the value of the PDF. It's not, I guess, strictly speaking, it's no longer the probability, it's the PDF at that value. Okay. Which you can say is proportional to an infinitesimal region around that value.
That can be any prior value. Can be like substituted with very small.
No. Once you have the normal and given any x5 equal to this thing, you can just consult that normal distribution, right? So you're basically looking at the PDF at that for that Gaussian. Okay, so hopefully you saw the email. You can bring any notes you want. No electronic devices.
You bring calculator?
Yeah, you bring your calculator. Okay, you can use the electronic device as a calculator. Okay, but you get the gist. I don't want you to be talking to each other or visiting websites.
No. Do we have to do the Gaussian cost calculation when since maybe we could
Yeah, we'll stick with.
can we just represent with some other functions? So the function.
Or I will give you information on this.
Professor, you have some question regarding the midterm grade. Should I just order a,
Oh yeah, do a regrade, whatever.
a regrade request on
The regrade request
on the
on.
grab scope? Okay.
Yeah, actually, so everyone, if you have any regrade request on the midterm, do it within grade scope. And I think I set the deadline for it end of this week. I think something. So there's a button there where you can request the regrade request. Okay, but just remember, please don't do it unnecessarily because I'm going to then regrade and it can go the other way also. So.
Question about the homework. Since it's done in groups of 3, are we just turning in one file for all 3 of us?
Yeah.
Oh,
Actually, I set it in the group submission
Oh, okay,
there.
I did.
So I don't have the students view there,
Uh-huh.
but hopefully. it
Yeah,
can
the
show-
report was done in that way too, right? Okay,
Yeah.
okay. So next.
Yeah.